Welcome to an IB Physics Review screencast. Here we're going to be going over dealing with forces at angles, dealing with forces when force is applied at an angle, and also dealing with the inclined plane when everything's on an angle. So the situation where this might come up is an example problem like this. We have the classic box being pulled along the floor, but my applied force is at an angle here. This can create an issue because what we typically want to do in these problems, we want to work completely horizontally and set up a net force equation where I sum my horizontal forces, or work completely vertically and set up a net force equation where I sum all of my vertical forces. For example, the normal force and the force of gravity. The angles force causes an issue because it's a little bit of both. The force is to the right and the force is also up. So I can't do any net force work yet because to set up an equation I need to be all horizontal or all vertical. So what I'm going to need to do is to break this into components. So we're going to look at a problem like this where I pull the object at an angle. It slides over to the side, creating a force of friction. So I have a bunch of different forces going on, and we'll look at how to deal with this angled force. What we have to do is to resolve a force into component vectors. The idea will look like this. If I have a force F, again, this is one that's up and to the right, but it could be in any angle. I can break it into two components, the two pieces that make it up. There's a horizontal piece to this force, and there's a vertical piece to that force. And we draw it like this. We create a right triangle where my right angle is here. And with that right triangle, I can do some trig, I can do some right triangle math, and solve for what I need. One thing I can do is do Pythagorean theorem. I have a right triangle, so I can do a squared plus b squared equals c squared. But what we can also do is do some trigonometry, and that's what we're going to look at here. So looking at our example, we're going to have two pieces. We're going to take the applied force and break it into a horizontal component. We'll call it FAX for the X piece of the applied force. And we have a vertical component, which we'll call FAY, the Y piece of the applied force. The idea is these two forces together will replace the applied force. So we can imagine that we're getting rid of this force, replacing it with these two forces because they're equivalent to the applied force. They together make up the same thing as the applied force. So what I'm going to do is do some trig. We can use Sohcahtoa, the trigonometry idea is to say, here's my angle. The y component of that force is opposite the angle. And so if I know that and the applied force itself is the hypotenuse, I can say sine is opposite divided by hypotenuse. In other words, if I solve for the y component, the y component of the applied force is equal to the applied force, the hypotenuse, times the sine of the angle. I can do the same thing for cosine. Since my x component is adjacent to the angle, it's next to it but not touching the, but it's not the hypotenuse. I can do cosine is adjacent side divided by the hypotenuse and solve for my x component. These are very common. This is how these usually work out as long as we're looking at the same kind of drawing with the angle in the same place. You can use the early part of your data booklet in section 1 has an example of vectors split into horizontal and vertical components using sine and cosine. So that's a reference there. If you have trouble with Sohcahtoa, make use of that. But this is how we break it into two components. And now we'll look at how we can use these two components to set up a net force problem. So here's just some example values that we can use: the mass of the box, the applied force. If I want to go through and solve a net force equation, now it's exactly like all my other net force equations. I can start with my net force in y. And to do that, I can sum all of the vertical forces. And now there's 3. There's a normal force is vertical. There's a force of gravity that's vertical. And now this y component of the applied force is vertical. Those are my three vertical forces. Now it's just a regular net force problem, just like every other one we do. We say up is positive, down is negative, so I assign pluses and minuses to my vectors here. Fg is negative. And we always say take the net force and set it equal to mass times acceleration in that direction. Don't forget this is vertical acceleration. In a lot of problems like this one, if the object isn't moving vertically, then its vertical acceleration is 0. So here we're just going through and looking at how some of the forces are related to each other. And I can start substituting in and solving for what I need to solve for. Notice here this is an example. When I have a force at an angle, the normal force isn't equal to the force of gravity. The normal force doesn't equal mg. It's less than mg because I'm helping out, in a sense. The applied force is pulling up a little bit, so the normal force doesn't have to push as much to counteract gravity. So this is specific to this problem. This is not always going to be true, but this is an example of how you could set up a net force in the vertical direction using component vectors. And of course we can plug in numbers and solve for the normal force. For part B, if I want to look at the dynamic friction, then I'm looking at something horizontal. Friction is a horizontal force. So I'm going to sum my horizontal forces. Remember, you always want to set up two net force equations, depending on what you need, but up to two equations where we sum the horizontal forces by themselves, or we sum the vertical forces by themselves like we just did. So here I have two horizontal forces. Again, there's a force of friction to the left, so I'm going to say negative for that. And my x component of the applied force is the other horizontal force. So we're ignoring Fa, the angled force, because we replaced it with those two component forces. Now, same as before, I set the net force, the sum of all the forces, equal to mass times acceleration in the direction I'm looking at, which is horizontal now. We plug in what we know about the x component with our trig. We use our net force equation here, and we can solve for the coefficient with some algebra. So those are two examples of using an angled force, breaking it into components, and dealing with a net force problem. All right, the other piece is dealing with an object on an inclined plane or an object on a ramp. This becomes a little tricky because I have lots of different things going on now. I have lots of angles going on. If I wanted to deal with it traditionally, I would draw my different vectors on the object just like normal. I draw an FBD. And so there's a couple forces acting on this object. There's the weight, or the force of gravity, mg, however you want to label it, but that always acts straight down towards the surface of the planet, towards the center of the planet, really. So we always draw it straight down. It doesn't matter that it's on an angle because the force of gravity pulls it straight vertically down. But we have a normal force, and the normal force is different now because the normal force is perpendicular to the surface. You want to remember the normal force is the force from a surface, and so the surface is pushing against the box at an angle based on the angle of the ramp. So it points directly away from the ramp, perpendicular to the surface of the ramp. And as this object, if we release it and let it slide down, there will probably be a friction force. There could be an applied force up or down the ramp. And I also have an acceleration that's angled down the ramp. So I have all these different angled forces, and especially what makes this tricky is the acceleration is at an angle. That's really hard to deal with. So what we do instead is we tilt the coordinate system. We decide to look at two dimensions where one is parallel to the ramp, which we can still call x. Sometimes we'll call it parallel. And one is perpendicular to the ramp, which we'll call y. Or we could call this the perpendicular direction. The idea here is that it makes life a lot easier. It might seem weird at first, but now the force of friction is in the x direction. The normal force is in the y direction. And the acceleration is even in the x direction. So my acceleration is not at an angle anymore, which is really nice. The only force that's at an angle now is the weight, the force of gravity. So that's the only force I have to split into components now. To do that, we're going to draw it like this. We're going to break the weight, the force of gravity, into its two components, parallel to the ramp and perpendicular to the ramp. The one tricky thing about this is your right angle is here, between the two components. The right angle is always between the two components. A lot of students draw it down here, but that's not right. The right angle is between the x and y component, or the perpendicular and parallel component. So we can talk about the weight perpendicular to the ramp. This is the force of gravity. You can think of it like this is the part of gravity pushing the box down into the ramp. And then there's a parallel component, or an x component. That's the piece of gravity pulling the box down the ramp. One thing to memorize is that the angle of the ramp, the angle of inclination, is equal to this angle in this little triangle we've made. And you just want to remember that that's how they work out. So now we can do trig again. You'll notice that what happens is a little bit different here because the triangle looks different. But I can still do Sohcahtoa if I want to talk about Wx that's opposite the angle. So I can do sine is opposite divided by hypotenuse. In other words, Wx, or sometimes we'll call it W parallel. This symbol represents parallel. And W parallel, the parallel component of the weight vector, is equal to the weight times the sine of the angle. I can do the same thing for y. Here I have my perpendicular symbol. And so I can use cosine because that's adjacent to the side. So W cosine theta, remembering that weight is equal to mg, so mg cosine theta is the amount of the force of gravity pushing the box down into the ramp. These are also worth maybe memorizing. On an inclined plane, this will always be the case. Mg sine theta is the component of gravity pulling the box down the ramp. Mg cosine theta is the component of gravity pushing it into the ramp. And now I can do a net force equation in the same exact kind of way. We're still summing an x or summing an y, or sometimes just to show both types of notation, and you can use whatever you prefer. We'll say the net force parallel to the ramp is what this says. Or in other words, the net force in x. There's a force of friction acting up the ramp, and the parallel component of the force of gravity, Wx or W parallel, whichever you prefer, is down the ramp, so we can call that negative. And now we can substitute in and solve for whatever we need to solve for. I can also do the net force perpendicular to the ramp, or this would in other words be the net force in y. And here I have the normal force acting up in the positive y direction, we could call it, and I have the y component of the force of gravity acting down. So again, I can substitute in what I know. So there you have it. That's how we set up these equations for angles in both cases, whether it's just one force at an angle or whether the whole problem is on an angle. Always remember to just draw your right triangles, draw your full FBD, and split the problem into two parts, the horizontal part and the vertical part, or in this case, the parallel part and the perpendicular part. If you set those up, let your FBDs and your net force equations do the work, then everything will fall into place after that. So go ahead and try some practice yourself, see how it goes. Have fun.